Hello. A lot of how the operating system works depends on the underlying hardware. Essentially, as we've seen in the previous video, the operating system is in charge of managing the hardware. So, before we go any further with how an operating system works and how the OS functions, let us take a brief background about the PC hardware. Essentially, we will look at how a computer hardware is designed. So, we know that the heart of any system is the CPU, and the CPU is interfaced to several devices such as the VGA card, a hard disk, a keyboard, RAM, mouse, and so on. Now, in order that all these devices work with a single processor, what is required is addresses. Essentially, each device in the system would have a unique address, and it is ensured that no two devices in the system would have the same address. For instance, we would have the hard disk, which is present from the address range 0x1F0 to 0x1F7. So, what this means is that when the processor sends out an address on its address bus, the hard disk would identify that the address is within this particular range, and therefore, it will respond. All other devices will then ignore that particular transfer on the processor bus, because it does not fall in its particular address range. For example, if the processor puts out the address 1F2, then only the hard disk will respond, because 0x1F2 falls within this particular range of the hard disk. So, if you look at something else like the mouse, which has an address range of 0x60 to 0x6F, it is not going to respond to the processor's request. Now, in systems, there are three types of addressing which are generally used. One is called the memory addressing, next is the I/O addresses, and the third is the memory mapped I/O addresses. So, we will look at each of these types of addresses more in detail. So, let us start with the memory addresses. So, the memory addresses, and most systems would have a large amount of such memory addresses, correspond to addressing the RAM. Each memory unit in the RAM is given a unique address. For instance, a RAM in a typical Intel system with 32 bits could be of size at most 2 power 32. That is, a Intel system with a 32 bit processor could have at most 2 power 32 or 4 gigabytes of RAM. So, each and every memory unit in this RAM has a unique address. So, this memory unit could be as small as a single byte, or in some systems it could be a word, that is, it could be of 16 bits or 32 bits. Now, how is this RAM used? So, essentially the RAM is configured in this particular way as shown over here, and this configuration is especially for IBM PC compatible Intel machines. So, this RAM, as I mentioned, has addresses to access each part of the RAM, and the RAM could be as large as 4 gigabytes. The addresses from 0x0 to 640 KB, represented in hexadecimal as A followed by 4 zeros, is known as the low memory. So, in this particular memory was used in legacy computers like the 8086, 8286 and so on. So, the old operating systems like MS-DOS would use this particular low memory. So, above this low memory from 640 kb to 768 kb, all addresses would pertain to the VGA display. So, in again this is an legacy issue where this particular area in the memory would correspond to the VGA display. This means to say that any ASCII characters placed in this particular area would then be taken by the video card and displayed onto the screen. The region from 768 kb to 960 kb was known as the 16-bit expansion ROMs. So, these also were legacy aspects present in legacy computers, and it is pertaining to every device that is used. Essentially, in the previous generation of computers in the early 80s to early 90s, the devices that were attached to the computer could have what was known as expansion ROMs. ROMs are the read-only memories, and these ROMs could be accessed, or rather these ROMs could be addressed within this particular memory region. Now, what is important for us and what we still use in the present Intel systems that we use for our desktops and laptops is this particular region from 960 kb to 1 MB. So, this was where the BIOS resides. So, as many of you would know, so BIOS is the basic input output system, and it is a read only memory which is present on your system, and it ensures that your system boots correctly, and it also ensures that your operating system gets loaded. So, the area of the RAM, essentially all memory addresses below 960 kb, is typically not used in modern day systems, while the area from 960 to 1 MB, that is 960 kb to 1 MB, is used by the BIOS and only used during the booting of the system. What is actually used in modern day systems is the RAM above this 1 MB region, that is starting from what was known as the extended memory, and this extended memory could go as far as the amount of RAM is present in the system. For instance, if you have 4 gigabytes of RAM or 8 or 16 gigabytes of RAM, then this extended memory will extend up till that particular region. The paths or the addresses above this RAM area will be generally unused. So, as we will see in the later classes in this particular course, we would see how the operating system loads itself starting from this 1 MB region. We would also see how the BIOS is going to be used to boot the operating system. Now, as we know, this particular RAM is also used to contain various aspects of the applications that we execute. For instance, the code segment or the instructions present in the program that you execute, the heap, the stack, as well as the operating system reside in this particular memory. Essentially, all of them will reside above this extended memory part. The next type of addressing is the I/O addresses. Essentially, in legacy computers like the 8086 and the 8088 and 8286, there was a separate memory region for devices, I/O devices like keyboards, mice, hard disks, and other programmable devices like an programmable interrupt controller could be mapped. So, unlike the previous addressing that we seen, that is the memory addressing. So, the I/O addressing could be from 0 to just 2 power 16 minus 1. So, this is roughly around 64 kilobytes, and the IBM PC standard would define what the use of certain addresses are. So, the IBM PC standard is a standard which was followed to develop systems like especially the desktop systems and certain servers, and this standard mentioned what devices should be present in what I/O addresses. For instance, it mentioned that the keyboard should be present between 60 to 6F. So, the I/O address 60 to 6F. In a similar way, the DMA controller would be present from C0 to DF. So, the other things like a SCSI or a hard disk, a primary hard disk present in your system will be present from 1F0 to 1F7. So, in this way several devices had very specific addresses in the system. So, what is the use of having such a specification is that we obtain compatibility. So, even now when you boot your laptop or your desktop PC, which is an Intel system or an AMD system, the BIOS will expect several things, like it will expect that there is a keyboard which is connected to your system, and the keyboard is present, or rather the keyboard is accessible from the address range 60 to 6F. Similarly, it would expect other things like the programmable interrupt controller to be present from the I/O addresses 20 to 3F. Essentially, what is maintained even in the modern systems is the backward compatibility to the old computers that were used. So, the memory addressing, as we have specified over here, even though a lot of it is legacy and was used quite a bit in the early 80s and 90s, even now, since Intel and IBM followed the backward compatibility, a lot of the systems that we use for our laptops and desktops still follow this particular hierarchy. Now, one problem which was noticed with this type of I/O addressing was the limited amount of address range that was permitted. So, for instance, over here we had at most 64 KB of addresses that could be present. So, this means that the number of devices that could be connected to the system through the I/O addressing was limited. In order to extend this, what was used was known as the memory mapped I/O. In this particular memory mapped I/O, hardware devices would then connect or would then map into regions in the memory addressing itself. So, as we have seen before, the RAM or the random access memory of the system would be addressed from the location 0 and extend upwards until the end of the RAM. So, typically in the systems of the early and late 90s, we would have something like 256 MB, 512 MB, or at most 1 GB of RAM. So, the space above this was unused. So, what devices would do is they would map a certain region in this particular part of memory into their devices. What this means is that when the processor generates an address in this upper region of memory, that is a high address in this upper region of memory, then that particular address would be directed to the specific device and not to the RAM. So, we have seen various address ranges that have been allocated to RAM, such as the low memory region, the location where the BIOS should be present, the location where various devices like the keyboard, hard disk and so on should be present. Now, who decides these particular address ranges? Essentially, these address ranges have been decided by standards, and a lot is impacted by legacy computers of the 80s and 90s. So, one very famous standard was the IBM PC standard. Essentially, this particular standard was fixed for all PCs, that is, all personal computers right up from the 80s would be compatible with IBM PCs standard. Again, even many of the systems that we use today, that is our Intel and AMD laptops as well as desktops, are backward compatible to this IBM PC standard. So, the reason for this IBM PC standard, or for that matter why a standard was required, was to ensure that the BIOS and operating system is portable across platforms. So, for instance, if I would write an operating system today, my operating system would know exactly where the keyboard should be present, irrespective of what IBM PC compatible system it is going to be loaded on. So, I could make a lot of assumptions about where various devices are present in the system. So, having such a standard would essentially ensure that the software that we write, especially the software that interacts with the hardware, such as the BIOS and the operating system, will be portable across several different platforms. The other way in which addresses are decided upon is by something known as plug and play. So, plug and play devices do not have any fixed address location, as we have seen for things like the keyboard or VGA memory and so on, but rather when the system boots and when the BIOS begins to execute, the BIOS would then detect the presence of some particular hardware in the system. For instance, the BIOS would detect that the system has a network card present. It would then ask the network card as to how much memory it requires and what type of memory it requires, whether it is a IO memory or a memory address. So, based on this, the BIOS would then allocate a portion of memory for that particular network card. So, the allocation would be fixed for each boot of the PC, but on the other hand, the location in the address map would vary across each boot. So, this particular slide here shows how a typical PC is organized. So, we may have multiple processors present in the system. So, this could be either one processor, two processors, three or four or and so on. So, it could also be possible that each of these processors have multiple cores inside them, and each core has 2 or 4 threads. Now, all these processors are connected to each other through what is known as the front side bus. So, there is always a sharing between all processors with respect to the front side bus. Now, an important device which connects to the front side bus is known as the north bridge or the chipset. So, the north bridge would interface with the memory through what is known as the memory bus, and it also interfaces with the PCI bus. So, on the PCI bus, you could have several devices like the Ethernet controller, USB controller, and the USB controller could have many USB devices which you see at the front or the back of your desktop. Now, as you would notice over here, the USB devices are connected in a tree like structure. Now, the PCI bus also has an hierarchy type of structure, and each bus, for instance in this case PCI bus 0, which is the closest to the north bridge, and you have in this way a PCI bus 1 which is connected to the north bridge through the PCI bus 0. So, the interface between bus 0 and bus 1 is through a PCI to PCI bridge. In addition to this, there is what is known as the south bridge, and this is south bridge interfaces with the PCI bus, or you could have a special protocol or a special connection with the north bridge, which is known as the DMI bus. So, in the south bridge, various legacy devices like the PS2 devices, keyboard, mouse, PC speaker and so on are connected. So, let us start with how x86 or the Intel x86 processors evolved. So, it all started with the 8088 processor or the 8088 processor as it was generally known as. So, this was a 16-bit microprocessor which had a 20-bit external address bus and therefore could address up to 1 MB of memory. So, how did we get this 1 MB? Is essentially 2 power 20. So, that 2 power 20 is 1 MB. So, the registers within the 8088 were 16-bit and it could be divided into various types such as the general purpose registers, that is the AX, BX, CX and DX. We had pointer registers which were used to, for instance, to point to strings which are stored in memory. So, these were the base pointer, stack index, destination index and the stack pointer. So, as we know that the base pointer is used to point to a frame present in the stack, while the stack pointer is used to point to the bottom of the stack. Then we have the instruction pointer which points to the instruction that is being executed, and you have several segment registers such as the code segment, stack segment, DS and ES segment registers. Now, in order to load or store an instruction or data in memory, what we would what the 8088 processor would do was it would take the segment base, that is one of the segment registers which forms the base, it would left shift it by 4 and add an offset. For instance, in order to fetch one instruction from the memory into the processor, the CS register would be used. So, CS register would be the base for the code segment. It would be left shifted by 4 and the IP or the instruction pointer would be added to that. In this way, even though there are the registers used are 16-bit, so each of this registers CS and IP are 16-bit, still by shifting it by 4 bits and adding the IP, it was possible to address 2 power 20 memory locations. One big step in the Intel systems came when the 386 was invented in 1995. So, these are 32-bit microprocessors. So, this particular processor had a 32-bit external address bus. So, therefore, it could address 2 power 32 memory addresses. So, this was 2 power 32 is 4 gigabytes of memory. So, what this means is that a system could have up to 4 gigabytes of RAM present in it. Now, the same amount of registers which were present in 8088 are also present here, except that now it is extended from 16-bit to 32-bit, and because of this extension, the registers are called EAX, EBX, ECX, EDX, EBP, ESI, EDI and so on. There were also a lot more features like the protected operating mode as well as virtual and segmentation schemes which were present. So, one thing you would notice is that while all the registers were extended to 32, the segment registers continued to be 16-bit. Now, Intel ensured that even though we switched from a 16-bit processor to a 32-bit processor, still backward compatibility with the old 8088 systems was maintained. This meant that any software which was written in an 8088 or 8086 processor would straight away run in an 8386 without much of a problem. To ensure this, even though the registers were extended from 16-bit to 32-bit, still programs could access the registers as if there were 16 bits only available. For example, the AX, BX, CX, DX would access the lower half of the extended registers, that is registers from 0, register bit 0 to the bit 15. So, these particular features in the 386 processor was taken forward to the 486 Pentium and so on. Now, more recently in 2003, there was the next big step in the x86 evolution. So, this was when the AMD K8 was introduced. So, this K8 moved from a 32-bit processor to a 64-bit processor. As a result, the registers which were known as the extended registers and were of 32-bit were now extended further to 64 bits. So, the EAX register, which was previously called in the 32-bit platforms like the 8386, was now called the RAX register, which essentially was for 64-bit. So, in this way other registers were also extended to 64 bits. So, in spite of extending from 32 to 64, the companies Intel as well as AMD ensured backward compatibility. That is, a program written in 8088 would still under certain circumstances will be able to run in the 64-bit platforms as well. Okay. Thank you.